Welcome back to Metaphor Math, and we're on to problem 1b here, where we're verifying that this is a metric space. And I'll remind you that a metric space is a set together with a rule, where that rule assigns a real number to each pair of elements in that set, and that rule we can think of as a notion of distance, and that notion of distance, that rule, must satisfy these four properties here. And before we get started with proving that this is a metric space, we need to make sure that we can talk about the least upper bound of the absolute value of the difference of x1 minus y1. So here I'll remind you that the set that we're talking about in our metric space is the set of all infinite sequences of elements of R, and our rule is the least upper bound of the difference, the absolute value of the difference between corresponding elements in two different sequences. But we don't know that this set is is bounded from above yet. And therefore, if it's by the least upper bound property, if a set is bounded from above, it must have a least upper bound. So I actually proved that given any two sequences that are bounded, if x is bounded and y is bounded, then the set x1 minus y1 and so on, x2 minus y2 and x3 minus y3 and so on, the absolute value of those differences, that set is bounded from above and below. I actually have a separate video proving that. I'll link in the top right corner here and also in the description. But let's suppose that we know that it's bounded, and therefore we can talk about the least upper bound. Therefore, we have permission to talk about the least upper bound. So now let's go on to prove that this metric satisfies the four properties of a metric space. So for property 1, we need to prove that the distance between any two pair of points is greater than or equal to 0. So to do that, we know that the absolute value of the difference between xi and yi is greater than or equal to 0, because xi minus yi is a real number, and for any real number, the absolute value of a real number is greater than or equal to 0. So that's nice. And we also know that the least upper bound of this set, which I'll call u is equal to the least upper bound of the set x1 minus y1, and so on. We also know that u is greater than or equal to any element in this set. So we know that it's greater than or equal to xi minus yi for any I in the natural numbers. And this bolded in is the notation for shorthand notation for the natural numbers. So we know that u is greater than or equal to xi minus yi for any I, because it's by definition of it being an upper bound. So therefore, since xi minus yi is strictly greater than or equal to 0, by definition of absolute value, therefore we can say that u, which is the least upper bound of this guy, is strictly greater than or equal to 0. And therefore, since u is the least upper bound of x1 minus y, the absolute value of x1 minus y1, therefore u is equal to the distance between x and y. So therefore, the distance of x and y will always be greater than or equal to 0. And we've proven property 1. Okay, so let's go on to property 2 here. We need to prove that the distance between x and y is equal to 0 if and only if x is equal to y. And in order for two sequences to be equal, then that means that each corresponding element in the sequence, just like vectors, just like how we talked about before, if two vectors are equal, then each corresponding element in the vector has to be equal to each other. So, it's the same way we define equality of sequences in the same way, where if x is equal to y, then x1 is equal to y1, x2 is equal to y2, and so on. So, and also remember that when we prove an if and only if statement, we have to go both ways. When I say that, I mean I have to prove both if dx comma y is equal to 0, then that means x is equal to y, and then I go the other direction. I have to prove, supposing that x is equal to y, I have to prove that that implies that the distance between x and y is equal to 0. So let's go the rightwards direction first, where I first suppose that the distance between x and y is equal to 0. So let's do that. So let's first suppose that dx comma y is equal to 0. Well, that implies that the least upper bound, by how we define this distance metric, the least upper bound of x1 minus y1, and so on, x2 minus y2, and so on, is equal to 0. And by definition of least upper bound, that means that 0, since that's the least upper bound of this set, 0 is greater than or equal to, by definition of an upper bound, any arbitrary element in the set. Any element in the set. So that means it's greater than or equal to xi minus yi for all I. Now, by definition of absolute value, xi minus yi must be greater than or equal to 0 for all I. If xi minus yi, suppose that xi minus yi is equal to 0, is strictly greater than 0, because there's only two possibilities for xi minus, the absolute value of xi minus yi. It can either be strictly greater than 0 or equal to 0. So suppose that it's strictly greater than 0. Well, that implies that we have an element, that implies that there exists an I such that xi minus yi is strictly greater than 0. But remember, 0 is our upper bound. So 0 must be greater than or equal to all elements in this set. But if I were to suppose that xi minus yi is strictly greater than 0, then I've just found an element that is greater than the upper bound? That's impossible. That's impossible. This implies a contradiction. Therefore, we can't have an element that is strictly greater than 0 in this set. Therefore, all elements xi minus yi must equal 0. And this is by definition of, or not by a property of absolute value. Remember, an absolute value of an element is equal to 0 if and only if that element is equal to 0. So that implies that xi minus yi is equal to 0, which implies that xi equals yi for all I. And I should say xi minus yi is equal to 0 for all I, which implies that xi minus yi is equal to 0 for all I, which implies that xi is equal to yi for all I, which implies, again, by our definition of equality of vectors, which applies also to equality of sequences, sequences, that implies that x, the sequence x, is equal to the sequence y. So that's what we wanted. That's what we wanted in going this direction. So let's now go in the other direction. Where we suppose x is equal to y, and then we want to prove that the distance between x and y is equal to 0. So we know that the distance between x and y is equal to the least upper bound of x1 minus y1, the absolute value of, I should say, x2 minus y2, and so on. But since x is equal to y, each of the corresponding elements are equal. x1 is equal to y1, x2 is equal to y2, and so on. So that means x1 minus y1 is equal to 0, which implies that x1, the absolute value of x1 minus y1, is equal to 0. So all of these elements are equal to 0. So therefore, 0, we can say that 0 is an upper bound, of this set. This set right here, x1, the absolute value of x1 minus y1, x2 minus y2, and so on. But we need to prove that 0 is the least upper bound. So suppose there exists an upper bound, say a, that is smaller than 0. An upper bound of this set, right here, a, that is strictly smaller than 0. Well, if a is strictly smaller than 0, and xi minus yi is strictly greater than or equal to 0 for all I, then this implies that xi minus yi is strictly greater than or equal to 0, and 0 is strictly greater than a. So we found an element that is greater than our supposed upper bound that we are supposing exists. So therefore, if we were to suppose that an upper bound exists that is smaller than 0, we would arrive at a contradiction, because we can't have any element that's bigger than an upper bound. So therefore, contradiction, we can't have an element, we can't have an upper bound that is smaller than 0. Therefore, 0 is the least upper bound. And since the least upper bound of this set is defined as the distance between x and y, we have that the distance between x and y is equal to 0. Okay, so we've proven properties 1 and 2. We've gone both ways with property 2, and we've proven property 1. So now let's go on to property 3. Let's clear the board. So for property 3, we want to prove that the distance between x and y is equal to the distance between y and x. So let's do that. So the distance between x and y is, like we said, the least upper bound of the set x1 minus y1, and so on. And we also know the following fact. xi minus yi is equal to yi minus xi. I'll give you kind of a hint of what this argument is. So we know that xi minus yi, the absolute value of, is equal to xi minus yi if xi minus yi is strictly greater than 0. And that means that negative xi minus yi is less than 0. So this implies that yi minus xi is equal to negative yi minus xi, which is equal to xi minus yi. So, this is in parentheses, these aren't absolute value signs, these are parentheses. So that means, since xi minus yi is equal to the absolute value of xi minus yi, then we have that in the case where xi minus yi is strictly greater than 0, we have xi minus yi is the same as yi minus xi. And we can make the same argument for the case where xi minus yi is less than 0, strictly less than 0, or equal to 0. So the same argument holds. But moving on, so we have the fact that xi minus y is the same as, is equal to yi minus xi for all I. So therefore the sets x1 minus y1, and so on, is equal to the set y1 minus x1, and so on. Therefore, if two sets are equal, then the least upper bound of two equal sets is the same. So the least upper bound of this set is the same as the least upper bound of this set because they're the same set. So the least upper bound of x1 minus y1, and so on, is equal to the least upper bound of y1 minus x1, and so on. Implying, and since we define the distance as the least upper bound of the absolute value of x1 minus y1, and again we define the distance between y and x as the least upper bound of the absolute value of y1 minus x1, and so on, then we have the distance between x and y is equal to the distance between y and x, which is what we wanted, for proving property 3 here. The distance between p and q is the same as distance between q and b, aka the symmetry property. So we've proven that property 3 it holds for this metric space. So let's finally prove the triangle inequality, property 4. Usually the hardest property to prove, but in this case it's not too bad. So let me define a certain shorthand, a few things so that I don't have to write least upper bound of such and such and such all the time. So I'm going to say that let A equal the least upper bound of P1 minus Q1, and so on. P2 minus Q2, and so on. And in the same way, I'm going to let B equal the least upper bound of Q1 minus R1, Q2 minus R2, and so on. And remember, this implies that A is equal to the distance between P and Q, and B is equal to the distance, as we've defined it, between Q and R. Now, this means I can make the following conclusion. Check this out. A plus B, or rather, let me before I say that, since A is the least upper bound of this set, that means that A is strictly greater than or equal to Pi minus Qi for all I. And I can say the same thing, since B is the least upper bound of this set, then that means that B is strictly greater than or equal to any element in this set, so therefore it must be greater than, or sure, for all I in the natural numbers, I should say. And since B is the least upper bound of this set, it means it's greater than or equal to any element of this set, by definition of an upper bound, so therefore it's greater than or equal to Qi minus Ri for all I in the natural numbers. So therefore, remember, we have a very special property. If A is strictly greater than B and C is greater than or equal to D, then that means A plus C is strictly greater than B plus D. And the proof for this property can be extended very nicely and very easily to the proof for if A is greater than or equal to B and C is greater than or equal to D, then A plus C is greater than or equal to B plus D. The proof for this property right here, which I've proven in a separate video, which I'll link in the description and in the top right corner, extends very nicely and very easily to the proof for this property here. So I can apply this property right here to what we have here. So I can say A plus B is greater than or equal to Pi minus Qi. Excuse me, these are in absolute values, since these are elements of these two sets, respectively. So Pi minus Qi plus Qi minus Ri. But look at this. Look at this. Look at this absolute value property right here that we can apply. The absolute value of A plus the absolute value of B is greater than or equal to the absolute value of A plus B. So if we say that this is quote-unquote A and this is quote-unquote B, then we can say the following. We can say the following. That these guys are greater than or equal to, and I'll write this down here so I have more room, greater than or equal to, that this expression right here is greater than or equal to, by this property 3 of absolute values. This property 3 that I've written here of absolute values, these aren't all the properties of absolute value, but this is one particularly useful one, especially in proving and verifying metric spaces. So we can say that this is greater than or equal to A plus B, as I define it. So this is Pi minus Qi, I'll put this in parentheses, plus Qi minus Ri. And look at this. Since addition is associative, this is the same as Pi minus Qi without all the parentheses, and these Qi's cancel. So I have negative Qi plus Qi, and I have Pi minus Ri. Look at this. And this, remember, this property holds for all I. Since these two hold for all I, it follows that this holds for all I. So this all of these hold for all I, and this holds for all I. Therefore, A plus B is greater than or equal to Pi minus Ri for all I, and I should say in the natural numbers. In the natural numbers. And therefore, A plus B is an upper bound of the following set. P1 minus R1, the absolute value of, I should say, P2 minus R2, absolute value, and so on. But remember, the distance between P and R is equal to, P and R is equal to the least upper bound of this set. The least upper bound of P1 minus R1, and so on. Absolute values. And we know that if, by definition of the least upper bound, let's call this least upper bound, let's call it D. Oh no, not D, that might be confusing. Let's call it W. We know by definition of least upper bound that for any upper bound of this set right here, upper bound, we'll call it, I don't know, C. For any arbitrary upper bound of this set, since W is the least upper bound, W must be less than or equal to C. And we just said that A plus B is an upper bound. So therefore, W must be less than or equal to A plus B. But remember, A plus B are the least upper bounds of these two sets, which is also the distance between P and Q and R, respectively. So therefore, we can say the following. And W is equal to the distance between P and R. So we can say the distance between P and R is less than or equal to the distance between P and Q plus the distance, because that's equal to A, and the distance between, I define that way upstairs, and that's plus the distance between Q and R. And look at this. We've just proven that it satisfies the fourth property, the triangle inequality, and we're done.